Okay, so I'm going to go ahead and get started. We'll let some people kind of trickle in as we move forward, but I wanted to go ahead and welcome everybody to the first of our Boundary Layer Urban Meteorology and Land Surface Processes seminar series. Today's speaker is Francesca Lappin, and she is a second-year master's student working with Dr. Phil Chilson. Before she arrived here at the University of Oklahoma, she graduated from the Florida State University with her Bachelor of Science in Meteorology. So I'm just going to go ahead and let Francesca take it away. Please do remember to keep your microphone muted and all of that good stuff until we are ready for questions at the end.
All right, thank you so much. Thank you all for joining me. Today we're going to be talking about low-level buoyancy as a tool to understand atmospheric boundary layer transitions. So to start off, let's look at what the atmospheric boundary layer is. So it's the lowest few kilometers of the Earth's atmosphere which interacts with the Earth's surface. It responds to surface fluxes and changes in the surface properties. Turbulence often is a primary transport for heat and moisture and momentum into higher levels of the atmosphere, and it can be transported either through shear induced or convectively induced, as we're kind of seeing here. And this is just a typical daily transition of the boundary layer. The sun rises and heats the surface, and the surface produces convective thermals, and we get mixing throughout this layer. And then after the sun goes down, the surface radiationally cools, we get an inversion, and then we go into a stable boundary layer regime. And then these profiles are just what the temperature looks like through those different phases of transition. So the atmospheric boundary layer is very sensitive. It's sensitive to heat fluxes, moisture fluxes, changes in topography, for example, from rural to a more urban or built up, such that you can get gradients in different properties, and you get differences in your ABL height and types of turbulence. So to really accurately resolve the boundary layer, we would need recurring high-resolution vertical measurements. And let's see if we really have that. So we do have about kind of three major tools that we use to sample the boundary layer. First being radiosondes, which are nice because they're regularly deployed across the nation twice a day. But twice a day really isn't enough to capture all of the different nuances of the boundary layer. And you can't control the ascent rate for radiosondes, and they ascend too quickly through the boundary layer. Remote sensors have incredible temporal resolution, but they're a bit expensive, and there isn't a nationwide network, and some require a clear sky. Finally, aircraft have high temporal and spatial resolution, but we don't have them that often. They aren't available all the time and are really more reserved for field experiments. So we wanted a way to marry all of these pros and really limit the drawbacks. So we come to remotely piloted aircraft system, or RPAS, that are designed to sample the atmosphere. And we get a few key boons out of using RPAS. We get increased vertical resolution because we can control the ascent rate as we see fit. They're reusable. We can redeploy them after short periods of time, up to 15 minutes, which is really useful for continually changing environments and environments that are both dynamic and also can be a little bit unpredictable. It also reduces their cost. The measurements are very high quality. If we look at this figure that I got from Tyler Bell, you can see the amount of data that you get from just 2 radiosondes being deployed and then a surface station. And when you include what the data you get from RPAS, it is a much more continuous field in time and height. And if you look at the RPAS, which is the shaded field, and then these columns, which are actually the radiosonde data, you really can't tell the difference between the two measurements because they are very close in accuracy. And they can be rapidly deployed and relocated, which is Very helpful for convective environments where you might need to move to get a better position on the storm. So another a key component of understanding the boundary layer is understanding how high is the top of the boundary layer. And we want to know that because you're basically figuring out, well, how high can energy and moisture be transported aloft? And their depths can change over different land surfaces. And if you look at this figure, which compares ABL heights that are determined via a model and those via observations, throughout the daytime, you do get a little bit of disagreement between the two. And also, if you look at these error bars, when they have a 600 meter error bar, or 300 meter on each side, that is a very large degree of error compared to the overall depth of the boundary layer. And also, parameters often don't include information about stability, which have been shown to be useful, yet sometimes they're just not available. Bringing us to stability, I want to mention buoyancy, which is essentially just the stability within the atmosphere. CAPE and SIN are bulk parameters of buoyancy that are commonly used via severe storm forecasters, but buoyancy can also be used to understand aerosol dispersion through cities and various other types of land use. Positively buoyant thermals can induce turbulence and mixing. And then buoyancy has also been used to understand convection initiation, cold pool evolution, and the timing of low-level jets. So if we zoom out and kind of underscore why we want to know more about the boundary layer, it's because it transcends almost all sectors of atmospheric science. For numerical models, boundary layer parameterizations, if they aren't necessarily representative of the environment, will hinder climate models, weather models, and convective models. Boundary layer has implications on air quality. It has implications on low-level winds and vertical motion, which is very important for pilots, especially in smaller aircraft. And when we bring in RPAS, we get a new way to really sample the atmosphere, which can offer new perspectives on kind of classical meteorological problems such as tornadic versus non-tornadic supercells. So my motivations in the study began with finding if there are any precursors to convective initiation. It kind of moved into investigating buoyancy's evolution over cases of convective initiation and low-level jets. And then finally, to test if buoyancy gradients can be used to measure the height of the boundary layer. So this will bring us to our first field campaign, which is LAPSE-RATE, which occurred in the San Luis Valley of Colorado. It was 5 days of 10 teams joining together to utilize RPAS to kind of answer or investigate these three major questions of CI, cold air drainage, and boundary layer transitions. There are 9 different types of RPAS that were able to log over 1,200 flights. In addition to RPAS, there were radiosondes regularly released at Moffett. In tandem was clamps, which can provide atmospheric boundary layer up to 3 kilometers via a suite of remote sensors. And then the 2 types of RPAS used in this study were fixed wing, which can do horizontal transects at 1 level for temperature, pressure, moisture, and wind. For this specific talk, I will not be looking at the fixed wing RPAS data, but more focused on the rotary wing, which can also measure all of those variables at a fixed location up to 1 kilometer. The other field campaign we will be talking about today is Flux-Capacitor, which is essentially a proof of concept for the 3D mesonet, which is a proposal that the Oklahoma mesonet be outfitted with RPAS so that the ABL can be regularly sampled to attempt to fill that data gap. There were 24 hours of continuous flights of RPAS flying every 30 minutes and radiosondes released every 2 hours at the Kessler site, which is just south of Norman. A key point in this analysis is going to be there's a low-level jet that occurred during Flux-Capacitor around 400 UTC, which we'll look into. So the RPAS that was used to collect all the data in this study was the Copter Sonde. You can see the Copter Sonde here. It is designed, tested, and manufactured by CAS engineers. It is a quad rotary copter with a 3D printed shell where the suite of like 9 sensors, 3 of temperature, humidity, and pressure act as passengers within the scoop where they are protected from sunlight and residual heat from the motor. The scoop and all the sensors before they even go into the field are tested in the OCS calibration chamber, and we can see how the accuracies of the Copter Sonde measure against radiosondes actually in the Flux-Capacitor campaign. So we can get a preview of some of the data. These are temperature and dew point profiles from the 2 sites that CAS had at LAPSE-RATE. And you can see the evolution of throughout time and longitude. The data was processed to use only ascending data where we don't use any of the descending data. Data over duplicate sensors were averaged, and then the offsets were determined, or offsets from the calibration were applied, so we really get the most accurate data we can. As for the radiosondes, data was interpolated to mimic the sampling frequency of our RPAS. So buoyancy was calculated at each level using this formula, where your environmental temperature is this blue line, or the temperature measured by the Copter Sonde. Our parcel temperature is a adiabatically lifted parcel initiated using the lowest elevation temperature from the Copter Sonde. And as we see, the buoyancy becomes more positive throughout the day and begins to vertically mix and kind of grow in elevate, or the positive values will grow in elevation. As we go through this loop again, it kind of rises and continues to be nearly isotropic. And seeing that kind of well-mixed variable reminded me of 2 other variables, temperature and potential temperature, which become very well mixed in the boundary layer. And the point where it is no longer well mixed and there is a strong gradient, we can determine as the boundary layer height. So we wanted to apply that to our buoyancy profiles to see if it kind of followed a similar strong gradient, but strong gradient at the point of the boundary layer height. But for this case, it would be a minimum rather than a maximum. So now let's look at some of the data from Flux-Capacitor. This is temperature at the lowest elevation from the mesonet, Copter Sonde in black, and the radiosondes are the red dots. I wanted to show this because this is the data that's going to be initializing the parcel and affecting our buoyancy measurements. Initially, early on in the day, there's a bit of a warm bias to the Copter Sonde, which could have been caused by shell heating, but that goes away to really very little disagreement in the values later on in the day. We can also see that, like I mentioned earlier, at 4 UTC, there is a low-level jet that came into the area. 30 minutes after that, or an hour after that, the temperature rises, and that's because the jet initiates mixing of the air aloft to the air at the surface, which warms the radiationally cooled air towards the surface. So now we're going to look at potential temperature data from radiosondes at the Flux-Capacitor campaign. So we wanted to look at the radiosonde data so we can get the entire picture of what's happening within the boundary layer in time and height. So the contours are your wind speed, and you can immediately see the low-level jet shows itself shortly after sunset, all the way right up until before sunrise. Contours over that are potential temperature lines, and you can see as the day begins, there is a shallow, well-mixed layer potential temperature, which increases with height as the day goes on and as the surface becomes heated. And as we come just a few hours before sunset, the potential temperature lines show more of a stable boundary layer transition. So let's look at kind of this evolution in a slightly different light using integrated buoyancy, or vertically integrated buoyancy. The Copter Sonde, throughout the entire flight, the buoyancy levels calculated at each level were aggregated. For the radio sondes, for them to be really comparable, we wanted to only vertically integrate those values up until the flight ceiling of the Copter Sonde. And we can see that there are, to begin with, there's a rise in positive buoyancy, so it's a positively buoyant environment during the day, and then about 5 hours before sunset, we begin to see a steady decline in buoyancy to where it becomes very negatively buoyant, reaching a minimum at 3:30 or 30 minutes before onset of the low-level jet, which through mixing raises the buoyancy and continually raises it to approach near neutral conditions. So we want to break this data down and decompose it into its time and height components. So we have buoyancy as a function of time and height from the radio sondes and the Copter Sondes. And immediately you will notice that there is some negative space that we get in the Copter Sonde later in the campaign, which is just a function of poor flight conditions. We don't want to fly into a jet because it's dangerous to our pilots and to our equipment. But recently, a researcher in CAS, Ariel Jacobs, found that only 20% of the time will RPAS not be able to complete their flights due to weather conditions during the fall, which is when Flux-Capacitor happened. Something else that we can notice is that even though there is data missing, the two plots are very similar to each other in wind speed evolution and the buoyancy evolution. And you might notice that there is a pretty steady decline in buoyancy preceding the jet throughout the entire layer that the jet is present. And that can be caused by the sinking air as the jet arrives to the north of the sampling site. We get that sinking cooler air kind of stabilizing the region. Like I said earlier, it's proposed that buoyancy also becomes very well mixed during the day. We see that in these lines of constant buoyancy that are just completely vertical and extend almost all the way throughout the layer. In some instances, we cannot see where it extends to because it's past our flight ceiling. But I wanted to see how a buoyancy or a boundary layer height determined by the buoyancy would be compared to a more classical variable like temperature. So the blue lines are the buoyancy minimum method, and the red lines are the temperature maximum gradient method. And in the Copter Sonde data, we can see that there's a little bit more consistent boundary layer heights with time compared to the temperature data from the Copter Sonde. And those values pretty well agree with the values determined from the radio sondes. And this continues throughout. This is a bit of an issue we need to work through of the boundary layer heights being very small. We're very, very close to the surface when we're in a stable boundary layer regime. But overall, the buoyancy method from the Copter Sonde data reflects very well with the boundary layer, or sorry, radio sonde method or data. And we can also see that a few hours after the jet has been in the area, we have a rise in the ABL height that persists for a little bit before radiational cooling brings the top height down again. And we see that in the buoyancy method for the radio sonde data, but not so much the temperature. So right now, we're going to shift gears a little bit and head over to the LAPSE-RATE campaign. We'll be more focused on convective initiation, as you can see is occurring in this radar loop. But I want to point out some kind of unique features of the San Luis Valley. So it is a valley with mountain ranges surrounding it of an average of 4 kilometers. We can see that it is a pretty arid land type in the center of the valley, but with dapplings of irrigated croplands in different parts of the valley. The 2 cast sites are the Sawash site, or KO4V for short, and then the Moffett School, or just MOF for short. So to kind of slow down the radar loop, we're going to take a look at just a few of the key points throughout the campaign. So at 1715, we get convection starting to occur along the mountaintops. And then, KO4V is the red square. And then an hour and a half or hour and 15 minutes later, we get convection kind of moving in closer to Sawash from the north and the west. At 1915, flights ended at our Sawash site due to inclement weather. And we can see that there's convection surrounding. While there's no reflectivity shown directly over the site, keep in mind that radar coverage within a valley isn't necessarily going to show the base of a cloud, and especially when the radar is to the east of this valley. And then at 1947 or 1945 is when the last flight occurred at Moffett. And that's because there was some rain, but convection tended to stay more northwest of the Moffett site. So wanting to look at how buoyancy evolved and moisture evolved at those 2 sites to kind of see why there was a difference in convection. So at 1715, convection started or just north of the Sawash site. And during that time, during this 30 minutes, we get buoyancy rapidly increasing, or rapid destabilization of this environment throughout the entire profiling height, the entire 900-meter layer, and continues to be fairly high for the rest of the flights. As for the moisture, moisture is increasing with time, where we get a moist layer occurring at lower levels during this time, just an hour before convection really occurs at this site. So comparing that against the Moffett site, we don't necessarily see the same story play out. The environment begins to be very moisture rich, and as a result, the buoyancy never rapidly increases. There's not a strong destabilization period that we see, and that could have to do with the surface not heating as quickly due to the present moisture. And we get a typically, or overall kind of a drying period before or towards the end of the flights, whereas convection is moved into the area around 1945-20 UTC, and The profile is fairly dry and not very positively buoyant, which affected the storm in a way where it could have weakened slightly over the Moffett site, and the storm tended to propagate more northward and kind of away from the Moffett site. So keeping in mind that these two locations were only 27 kilometers apart, buoyancy and moisture are very sensitive in terms of spatial distribution. The evolution of the buoyancy and the moisture are quite different for the two, where you really do see a strong destabilization period through a large layer, which helped convection be sustainable as compared to an environment that doesn't have a ton of positive buoyancy and tends to be a little bit drier. And then this is a little bit different, but this is one of our cold air drainage days, where cold air descended down the walls of the valley and kind of filled up at the base of the valley, which creates a very strong temperature inversion and a very stable boundary layer. And we certainly see that with the buoyancy. There's a strong gradient with height. The values are strongly negative, more strongly negative than the positive ones for the convective case. And it takes a much longer time for there to be really convective mixing and heating and even small values of positive buoyancy. So we see a very stable case. But all in all, highlighting some of the things that buoyancy can do that other variables don't necessarily show. We can use buoyancy with promising results to determine the ABL height. It compares well, if not better, than the temperature in this specific case. And also we can see that there is a disruption in the typical ABL transition as a result of the low-level jet. As for CI, it's not necessarily that we found a precursor, but we've found differences in how the environments evolve and which leads to preferential convection in one area versus the other. Future work is going to be includes just using more cases, evaluating more cases to see if we see similar attributes, that kind of rapid destabilization before convection, or a slightly weaker but stabilization before a low-level jet. Also improving the buoyancy method to determine the ABL height. There are many things we can do to kind of make it a little bit more smooth or cleaner, but mostly giving an option to where if we don't fly past the boundary layer top, that we don't get a erroneous value, that it's just picking up because it satisfies the conditions. What else we're doing at CAS, and for me mostly, we will be doing flights at the airport to eventually assimilate data that we receive in that location to improve low-level wind forecasts and improve the understanding of the boundary layer, which can help aviation forecasts. So finally, I just want to acknowledge all of the people who have helped me get to this point. Thank you to the entire CAS team for collecting the data and processing the data from LAPSE-RATE and Flux-Capacitor. Thank you to my advisor, Dr. Phil Chilson, for helping me through all of this and really guiding me. I want to say thank you to Dr. Liz Pillar-Little for not only being an incredible role model, but keeping CAS together and not exploding. Thank you to Brian Green and Tyler Bell for really getting me acclimated into CAS and getting me started on my research journey, and also working through the LAPSE-RATE data. To my partner, David, he is a constant support system and always has my back and is very supportive in mental health struggles and every other struggle. To my roommate Anna, who has helped me improve this talk and just have been really supportive through the whole thing. And all my other friends and family, but mostly these cute little cats, Cheez-It and Ellie. Thank you all for joining me. I'll go back to my summary slide and then open it up for questions.
Thank you, Francesca. I always like a talk that finishes with cats, so it's always great. So we do have a good number of people on the meet, so I think the way that we'll go forward with questions is if you do have a question, you can either type your question into the chat, or if you'd like to unmute yourself and talk about your question, please just mention that you have a question and I will call on you from the chat box. So go ahead and enter your questions or raise your hand in the chat box. While we're waiting to see if anybody chimes in there, I had a question related to the buoyancy decrease that you noted prior to the low-level jet. Mm-hmm. We know that usually in the Great Plains, the flow is already southerly before a jet profile might emerge, however you define the jet profile. Is it possible that this is related to advection in that layer?
So while looking at the temperature profiles before the jet really came through, there is a temperature inversion for about the first 400 meters, which is kind of on par to the bottom of the jet. So I think that also has to do with it. It is possible that the advection of warmer air came into the area, and that's at a slightly higher level than the surface, which kind of strengthened that inversion and could have led to more negative buoyancy. But my buoyancy calculation doesn't include moisture, which is something we're going to add soon. So that might have also impacted it. I just wouldn't know for this specific analysis.
Understood. Thank you. I believe that Xiaoming has a question. If you want to unmute yourself, go ahead.
Yes. In this figure, in terms of daytime convective boundary layer height, between there is large difference between red and blue. This kind of don't look good because normally we have good understanding about the convective boundary layer. Using different methods to diagnose convective boundary layer height, normally the uncertainty is very small because on top of convective boundary layer, the inversion is very strong. So no matter use what kind of method, the uncertainty should be, I would expect uncertainty smaller than this one.
So for the radiosondes, it could have to do that it was a fairly windy day to begin with, so that there could be some impacts of it not being at just one location, which is why there might be big differences between the temperature and the buoyancy for the radiosonde data. Just that type of advection could have had an impact. As for the Copter Sonde, so with such high resolution data, we catch rapid changes in temperature, which if it is very low to the surface or something happens where there is a strong breeze, whether it be cooler or warmer, can affect how the max gradient is lower than what you would really expect But for the buoyancy, it isn't impacted as much, because the surface temperature should be reflective of those changes as well with the profile data. But yes, no, I do agree that they do have large discrepancies between the two.
And also, especially during the day, the red in the lower panel decreased to 200, 100 PBL height. That's very suspicious. Yeah, you may need to check your vertical profile is due to very noisy data or whatever.
So also keeping in mind that these profiles are every 15 minutes.
Okay.
And typically you don't need, typically in previous studies on the boundary layer height are over kind of wider time periods, not such rapidly measured values. So we could have more spikes than we would normally see with kind of wider spaced out data. And so that high spatial resolution, you could be picking up things like thermals, per se. But we are looking into trying to temporally average them so that they're more consistent with the value before it, and not going through those noisy jumps.
Okay.
Are there any other questions from the audience? Go ahead and chime in on the chat if there are. Go ahead, Petra.
Yeah, just to quickly follow up on a question from Xiaoming. It might be useful to overlay those boundary layer calculations on some of the time height cross-section plots of wind speed and temperature to get a better sense of, to basically see how your boundary layer height calculations then match up with the evolution of your wind and potentially also temperature profiles. So I was just wondering if you had done that.
No, I have not done that yet. It's a really good idea that I would like to look into. With so many